And I'll just first also thank Sasha and others for putting on these sessions. They have been really useful. And thanks for inviting me to give a talk in one. What I'm going to do is try and summarize and make some links between several studies which have involved lots of people, partly in Malawi, partly in northern Norway, partly in the lab in Utrecht. And this has been funded by various bodies, including NERC, EPSRC, and the ERC. And following the theme as Sasha outlined, I want to talk about inheritance and strain localization. And I should probably have put active early stage rifting on that title, just to make the point that compared to some of the later, or at least the last talk, I'm talking about relatively early stage of rift development. And just to take us straight to East Africa, and also just talk a bit about what I mean by influence of pre-existing structures and where that's coming from, although probably familiar to a lot of you. If you look at the East African rift, for example, here in Tanzania, it tends to follow, at least in map view, the trace of inherited foliations from various high-grade metamorphic events, mostly Precambrian. In this particular figure that I took from Corti et al.'s 2007 paper, you see how the rift system bends around the Tanzanian craton. We can zoom in on that. For example, in the northern part of the Albertine Graben, the graben is parallel to these basement structures that strike northeast and stops against some northwest trending features. Similarly, a bit more detail in northern Malawi. In the Karonga region, you can, Kolawole and others mapped out the Mugesa shear zone in white, or foliations in the Mugesa shear zone in white, and fault traces in black are roughly following the trend of those foliations, as well as being situated within that shear zone. So these very large, at this sort of scale, it's quite clear that there is some correlation between the location and orientation of rifting and the location and orientation of pre-existing ductile structures. If we zoom in a bit more, and this is work from Michael Hodges' PhD, and look at specific faults, then it's a little bit less simple. And that if we map out the fault trace of the Belilam Takataka fault, much studied, or now fairly well studied fault in southern Malawi, then the fault trace is roughly parallel to the general trend of foliations. But if you look at it in detail, you have segments like in the south here, where the foliations and the fault are roughly parallel, but then that changes into a section where they're relatively oblique, back to parallel, back to oblique, as you go further north. So it's not quite as simple as that the fault and the foliations have a one-to-one relationship. And even more if you look at it in 3D, so there's a couple of outcrops. Here is a location where the fault follows the foliation, and the foliation dips about 60 degrees, and the fault follows it, where you can see some cataclastic rock basically aligned to the foliation. But if you go somewhere else, you see wider zones of fractures, and the general trend of the faults here in blue is oblique to the foliation, which is here very gently dipping. So when we're thinking about what weaknesses affect the early stages of faulting in rift systems, then what are those weaknesses? At what scale and over what depth range do they actually affect the style of rifting and the type of faults and the orientation and location of faults? I made a suggestion a few years ago that there might be that these larger faults or larger border faults are related to deep-seated weaknesses, or where weaknesses transect the lithosphere, and then the smaller intrabasin faults are new structures that might have smaller scale and different orientations. But in Ebinger and others, in a recent paper showed that that's probably oversimplified, or it's definitely oversimplified, because they're seeing, at least in some locations in Malawi, where these cross sections are from, that the intrabasin faults also have deeper continuations and some seismicity in the lower crust, is aligned below intrabasin faults, while others is aligned below border faults. So there's no clear distinction between those different types of faults. So really this figure should have had some deeper intrabasin structures as well. So from that, we've looked a lot more detail recently at various fault systems in Malawi. This is a compilation of fault orientations from Williams et al. And here faults in red through southern Malawi. So this is the southern end of Lake Malawi. And you can see that these faults vary in orientation from northwest striking for the Belila and Takataka that I showed you earlier. And then as you go south, they bend to northeast striking and then back to northwest striking. So, and that's also shown by these rose diagrams on the right. Now, if there's a couple of ways you could explain that. You could have a rotation of stresses and faults forming optimally new faults, or you could have these faults reactivating various existing structures. But if we look at the stress field, this is a stress inversion based on a relatively small number of earthquakes, but it's the best we've got for this part of the rift. And if you do that, you come up with a roughly northeast or east-northeast trending least compressive stress. And if you put that on top of the fault system, you end up with that being oblique to pretty much all the faults. So it doesn't look like there's a particular orientation that's generated by a preferred orientation in the stress field and another that's based on reactivating structures. It more looks like everything is a little bit offset from an ideal orientation, but nothing is poorly oriented either. So there is possibility that all these faults are reactivating in a constant stress field. And that's kind of also shown by the orientations of joints. If you take those as a proxy for sigma 3 and say, well, sigma 3 is roughly perpendicular to the joints, then the main joint system is roughly consistent with this stress regime or something similar to it. And just to look at a bit more about the rocks these faults are forming in, a critical point here that we should emphasize is that none of these rocks are particularly weak. And the foliations are not obviously weak either. And the rocks are amphibolite to granulate facies, gneisses, and amphibolites. What's mapped as foliations is generally segregation bands or mineral orientations of relatively strong Bailey friction type things. And if you look at a fault zone in the field, it's not a localized slip surface on something weak. It's more of a broad gout zone that vaguely but not perfectly follows foliations. So these are mechanically relatively strong foliations. And if we go and look at a specific fault, if we go down to southern Malawi and look in detail at the Geolo fault, this is from Luke Wedmore's recent Journal of Structural Geology paper, then in that particular location, so down in the south here, you see in the topography, the Geolo fault as a major border fault, and there's not much happening in its hanging wall. A couple of little intrabasin faults, but nothing major. So this seems to be a more localized structure than some of the faults further north. And it also has an orientation that is northwest striking, which is parallel in this location to the dominant foliation, which is here marked in yellow dip and strike symbols. And it has some stepovers where scarps, marked in blue, are parallel to a dike system. So this fault basically has a strike that's similar to the foliation, and where there are linkage structures, they are parallel to dikes. So here there seems to be appropriate structures for reactivation. Whereas elsewhere, they might, well, it doesn't look like anything super poorly oriented are getting reactivated, but things that are relatively well oriented are. So the point I'm trying to make from southern Malawi, to sum those up, is that part of the southern rift, which is low strain, non-magmatic, have a surface expression that is broadly following Proterozoic ductile fabrics. But if you look in detail, the faults are favorably but not optimally oriented, assuming a uniform stress state. And if you look in more detail, then the foliations reactivated where it's well oriented, but where it's not well oriented, the faults are making their own way. So that's at the surface, which is an important point here when we're talking about the deeper earthquakes that are seen in many parts of the southern parts of the East African Rift. That could look a bit different from what we see at the surface. Again, if we look at the earthquake distribution, there are deep earthquakes below many faults. The rocks that's happening in have these relatively high-grade foliations. They are granulites and fibrillates seen at the surface, like this, where they're exhumed from depth. If you look at them in thin section, they're quite cohesive, made up of relatively strong minerals. If we look at these in experiments, you'll find that the more felsic rocks are velocity strengthening at mid to lower crustal temperatures. They're unlikely to create seismicity. Easier way to make seismicity is to have something mafic. This has been suggested before, but we checked this in the Utrecht lab led by Nina Hellebrekers in a master's study. And basically coming up with that, well, you need it, and at least under experimental conditions for these sort of temperatures, to get earthquakes, you need something more mafic, or at least something with some velocity weakening material at that condition. And one way of doing that is to have, you don't need everything to be mafic, you need some proportion. So if you have, like we do at the surface, a mixture of different rocks that have been superimposed in past orogenic events, then you might have a mixture of mafic and felsic material, velocity weakening and velocity strengthening material. And if you've got sort of above about 60% at tectonic, 60% mafic material at tectonic loading rates, that might just do it. Now, for the last couple of minutes, before I run out of time, I just wanted to compare this to an example of exhumed rocks in northern Norway, where these rocks have been exposed to rifting or normal faulting tectonics, I should say, at mid to lower crustal conditions. We know that from exposure of pseudotaculites that are formed at mid to lower crustal conditions in a mutually cross-cutting relationship with myelonites formed at lower crustal conditions based on the thermodynamics. Pseudotaculite here as an example, and Lucy Campbell has recently published on these rocks, highlighting that there are high strain zones within this lower crustal section. Those high strain zones are made up of mutually cross-cutting sets of normal sense and strike slip sense shear zones, but the larger ones are normal. In this sort of pattern where you have a few large shear zones, some smaller ones interconnected, and in general you end up with strong blocks surrounding by, or rigid blocks surrounded by these ductile zones. This photo was on the intro as well, but what I'm talking about here are ductile shear zones that localize into typically existing structures, such as dikes or fine-grained zones. And they are interrelated with these pseudotaculites that form more linear features, commonly cross-cutting any existing structure. So the ductile deformation is localized, the brittle on reactivating or by reactivating viscously weak zones. Brittle structures sometimes follow these zones, but quite commonly also don't. So a model for how these earthquakes in the lower crust preserve the pseudotaculites can form is that you have rigid zones surrounded by ductile shear zones. As the ductile shear zones move, you end up with a geometrical necessity of breaking the rigid blocks. They don't flow easily, and that's creating your earthquakes without needing to propagate from any faults above. So in this case, the high-grade foliations are weaken the viscous regime and controls deformation and creates brittle failure there. And the question is, well, can they also create or control the overlying brittle deformation in a system a bit like this? So think back to Malawi. We have systems where faults follow existing weaknesses if those are already well oriented, but otherwise they make their own way. But if you think of the same system in the ductile crust below, you might well have features there that reactivate weak foliations that are not necessarily weak in the brittle regime, and controls that deformation.
Yeah, I think you should come to
and
the
this is my final slide.
Perfect.
On cue there, Sasha. This is an image again then of the Geolo fault from Luke Wedmore's paper, saying, well, in the event that you have a really well-oriented structure, then that takes up all the deformation. And in the event, other examples where you don't have such a feature, distribution of strain in the upper crust may be a bit less simple. And yeah, I'll end there. And thank you very much.
Thanks a lot. We have time for 1 or 2 short questions. There's one in the chat by Winch. Would you like to ask the question yourself?
Okay, I can ask the question myself. Your lower crustal earthquakes are more than 25 kilometers deep. With a normal geothermal gradient, you should easily have partial melting. And in such a case, you might have hydraulic fracturing where the fluid pressure is provided by that melt. I wonder if you think that could be, that would also give you earthquakes in felsic crust. You don't need mafic.
That's possible. I can't write that off. There is no evidence so far for partial melt in any of the seismic studies of the region that I'm aware of. The thermal gradient in this part of the world is relatively low. It's lower than normal for continental crust. So that might be another argument against it, but it's not something we can write off. So that's a good point.
We have time for one short question. Megan.
Hi, Ake. Thanks for the talk. You know where the figure you were saying the rift kind of does this sort of jogs to the left and then comes down again. Do you know if the ductile structures have that kind of fabric there as well?
The ductile structures do the same.
Oh, cool.
At that scale, at least.